Welcome back to the podcast. Today, we're diving into the intriguing world of data encoding formats. We'll explore some of the most commonly used formats in software development, including Json, XML, CSV, and their binary counterparts. We'll discuss their strengths and weaknesses and how they play a role in data interchange between applications. So whether you're a seasoned developer or just curious about how data is structured, stick around as we unravel these encoding formats together. Let's start with two of the most popular formats, Json and XML. Both of these formats are great for human-readable text since they support Unicode character strings. However, they struggle when it comes to handling binary strings, those sequences of bytes that lack character encoding. To get around this issue, developers often encode binary data as text using base 64. While this method works, it does increase the data size by about 33%, which can be a considerable overhead. Both JSON and XML offer optional schema support, with XML schemas being widely used. However, many tools for JSON tend to skip this feature. This can lead to complications, especially when it comes to interpreting data types like numbers or binary strings, which rely heavily on schema definitions. Without schemas, developers often have to hard code their encoding and decoding logic, which can introduce errors and create maintenance headaches. Now let's talk about CSV. This format doesn't use schemas at all, meaning that the meaning of each row and column is left entirely up to the application. If you change your data structure, say by adding a new column, you'll need to handle that change manually. CSV can also be a bit ambiguous. For example, what happens when a value contains a comma or a new line? While there are formal specifications for escaping these characters, not all parsos implement them correctly, which can lead to inconsistencies. Despite these limitations, JSON, XML, and CSV remain popular choices for data interchange, especially between organizations. The reality is that as long as everyone agrees on the format, the efficiency or aesthetics of the data structure often take a back seat to the challenge of reaching consensus among different parties. When we zoom out and look at the bigger picture, it becomes clear that the choice of data format can significantly impact performance, especially for large datasets. This observation has led to the development of various binary encodings for both JSON and XML. Formats like MessagePack, Bson, and protocol buffers have emerged, aiming to be more compact and faster to parse, while also extending the range of data types available. Let's take a closer look at MessagePack, a binary encoding for JSON. For instance, if we encode a simple JSON record containing a username, a favorite number, and a list of interests using MessagePack, we end up with a much smaller byte sequence compared to the original JSON. The first few bytes indicate that we're dealing with an object that has 3 fields, while the subsequent bytes describe the lengths of the field names and their values, all encoded in a compact format. While binary formats like MessagePack offer space savings and potentially faster parsing, they do sacrifice human readability. This raises an important question. Is the reduction in size worth it if the data becomes less accessible to humans? Moving on to Apache Thrift and protocol buffers. Both of these libraries require a schema for encoding data, which adds a layer of structure. For example, to encode our earlier JSON record in Thrift, we'd define a schema that specifies the data types for each field. The encoded data then uses field tags, numerical identifiers, rather than field names, which helps keep the data compact. Thrift offers multiple binary encoding formats, including binary protocol and compact protocol. The latter is particularly efficient, packing the same information into even fewer bytes by using variable length integers and combining type annotations with field tags. Protocol buffers, developed by Google, follows a similar approach and can encode the same data in just a few bytes, showcasing the power of efficient data encoding. One of the significant advantages of using schemas in these binary formats is how they handle schema evolution. As applications grow and change, schemas often need to be updated. Both thrift and protocol buffers are designed to maintain backward and forward compatibility. For instance, if you add a new field to your schema, you can make it optional, allowing older applications to ignore it while still being able to read the data. However, there are some caveats to keep in mind. If you change a field's data type or remove a required field, you can run into compatibility issues. It's crucial to ensure that new fields have unique tags, as reusing tag numbers could lead to confusion and data corruption. Another interesting format to consider is Apache Avro, developed as a subproject of Hadoop. Like thrift and protocol buffers, Avro uses a schema to define data structure, but it offers two schema languages, one for human editing and another that's machine-readable. This flexibility makes Avro particularly well-suited for big data applications. In summary, while JSON, XML, and CSV are widely used for data interchange, each comes with its own set of limitations. As data needs grow, binary formats like MessagePack, Thrift, and protocol buffers provide more efficient alternatives, especially for large datasets. Understanding these formats and their schemas is essential for developers looking to optimize data handling in their applications. Thanks for tuning in today. We hope you found this exploration of data encoding formats enlightening. Whether you're working with small data sets or managing terabytes of information, choosing the right format can truly make a difference. Until next time, keep coding and stay curious.